Hi there. We're moving on now from the standard model, which obviously you've finished, thanks to all those who did the block test. We're moving on to the second subtopic. So we've got the big overall topic, particles and waves. We've got a number of subtopics. The first one was the standard model. This is the second one. And it's called Forces on Charged Particles. Now, once again, you need to take notes of everything I'm putting on my whiteboard as appropriate. At the end of the lesson, there will be a sort of run through of a quick, I'm calling them PowerPoint type presentations, where topics appear on screen, and you can follow those. If you find it easier to follow that, you can stop and start. This will go up again as a Google Meet and as a YouTube video. If you're following what's going on in the boat book, then the boat book is also divided into sections. They just start at number 1 and keep going. This is boat book section number 9. And in the boat book, the topics aren't numbered, they're actually lettered. So there's A to I, which if I count those up, A, B, C, D, E, F, G, H, I, that's 9 little parts to this subtopic. Okay, so they're in the boat book and you can follow them. I'm going to divide this first little bit into 2 sections. And this first section is called Electric Fields. The second section, which will be in another lesson, which is called Magnetic Fields. And I will make reference, although it's not part of the actual teaching, but I will make reference to another thing called gravitational fields, just because it's something that we are very familiar with, because we live in a gravity field, and you're obvious of what goes on in a gravity field. You pick up an object and you drop it and it falls to the earth. That's because we're in something called a gravitational field. So I'll keep coming back to this to provide a sort of reference point for something that you're familiar with. You won't be familiar with electric fields or magnetic fields particularly. You can't see them. In fact, you can't see a gravitational field, but we experience gravitational fields all the time. We don't really experience electric fields or magnetic fields too often. Probably the most common occurrence of a magnetic field is if you have a compass, if you're doing some hill walking and you're out with a compass and it will show you the direction. We don't directly experience magnetic fields particularly well. Some animals do. We have a large number of birds, for instance, that come here in the summer, and they go back to West Africa, for instance, in our winter, and they follow the Earth's magnetic field. So some animals can experience magnetic fields directly. We can't do that. We don't have the ability to know which way to go. So we're going to have a look mainly at the first 2. I will keep coming back to this one. I'm going to teach in a number of lessons. I'm going to step up the number of lessons. At the moment, well, going on the last couple of weeks, you had 3 lessons a week, and we were making steady progress on that. Although it was fairly steady, it was pretty slow. It's now become obvious that you're going to be at home for a longer period of time, so I've got to fit in more stuff. So the 3 hours that you have allocated at the moment is going to be extended. There's going to be more for you to do. You're going to get work which you should do in the designated 3 1-hour slots, but there's going to be extra stuff for you to do, which is going to be doing extra problems, perhaps going back over these notes, taking longer to make notes. And so that's going to get stretched out now. Now, if you were in school, you'd have 6 50-minute lessons, and then you'd be expected to do half an hour of homework a night, or something like 4 nights a week. So 6 50-minute lessons is at least 5 hours, and half an hour of homework 4 nights a week is another 2. So that's 7 hours. Now, you're probably not doing anything like 7 hours of work a week, because I've been trying to stick to the 3, but we're now going to have to start doing extra. So you're going to use your designated 1-hour slot, plus you're going to have to find some extra time to do things, just so we can get through the work, because if we carry on just doing 3 hours a week, we're not going to get through the course. Okay, so you've got that, and you should be writing this down in your notes as appropriate. Mr. Garrett's got his course notes that you can follow. Every now and again, we'll have a reference back to them, and we'll look at worked examples in Mr. Garrett's notes as well. So the same sort of thing that we've been doing over the last couple of weeks. Okay, so here's a question. What is a field? And depending on where you live, you might be able to look out the window and see a field. You know, if you live on a farm, you can look out the window and see it's got animals roaming around in fields, or you've got fields of grass. So agriculturally, you have a thing called a field, and it's just a space in which something goes on. You might grow some barley, or cows might wander around. So a field is just a space. In physics, a field is also a space. Now, it's not a space in physics where cows wander around or you grow grass. It's a space in which an object feels a force. So we're surrounded by a gravitational field which is invisible. You can't see it. But if you're standing on the ground like that, you're only standing there because gravity pulls you down. And if you've got an object and you let go of it, it's going to feel a gravity force, and it will fall to the ground. So in physics, a field is a space in which an object feels a force. A gravitational field exists around this person and the object, and when they let go of the object, it feels a force and it drops to the ground because it's feeling a gravity force. But we want to look at electric fields and magnetic fields. I'll keep coming back to this idea about gravity forces. So you can't see a field, you can only see the effects of a field. And what we're going to be looking at is what happens when you have small particles in a field. What happens when you have an electron in a field, or a proton in a field, or a neutron in a field? And it depends what sort of field it's in. As I said, we're going to look at these two fields, an electric field and a magnetic field. So this first couple of lessons is really just going to concentrate on an electric field. Okay. Now, here's a little bit of revision. You should know this, that there is something called a force between two charged objects. So if I've got two charged objects, like two negatively charged objects, here they are, each, regardless of whether there's a field going on or not, these objects set up their own field. It's like as if we're talking about an object in a gravity field. A gravity field is a thing in the big space. An object like a ball, for instance, does not set up very easily its own gravity field. It in fact does, but it's so small that you can ignore it. So we're not going to look primarily to start with at a bigger field. We're just going to look at the field around these small objects. Now, there's obviously a field that's around each of these objects because these objects are at a distance and the forces that they feel work at a distance. I don't have to go up to this object and push it to make it move. These objects feel each other's effect. And you probably know that two negative objects would repel each other. And that's because they're each setting up their own invisible field around them, and that's pushing them apart. You ought to know as well that if I've got a positive and a negative, they are going to feel the force around each other, and that's going to cause them to go towards each other. And the other one, which is very common, is obviously two positive charges, and they will repel as well. So we have a phrase is like charges repel. So a like charge, this charge is just like this one, and two like charges will repel each other. Two like charges, this charge is just like this one. So two like charges will repel each other, and the opposite phrase is unlike charges attract. So that's one thing we need to know. Now, neutral objects, they don't have a charge, so they don't do any attracting or repelling at all. It's only things that have a charge that actually have this going on. So if I had two neutral objects, they wouldn't do anything. They just sit there doing absolutely nothing. And most atoms are neutral and they don't do anything. They don't repel each other. They don't attract each other. But of course, you can change a neutral atom into a charged particle by ionizing it. So if a neutral atom loses an electron, then it becomes charged. It becomes positively charged. If it gains an electron, it becomes negatively charged. So you can think of these things, if you like, as you could think of that as like two electrons, if you like, or you can think of that as two protons. But we're just going to call them charged particles because they have a charge on them. And if it is protons and electrons, you should be aware that these particles have a charge of 1.6 times 10 to the negative 19 coulombs. That's the charge on a positive particle, like a proton. And the electron has the same charge, but it's just a negative charge. So a negative charge of 1.6 times 10 to the negative 19 coulombs on an electron, or a positive charge, just don't see the positive sign, but you could put it there. Doesn't make any difference. If it's not there, it's assumed it's a plus or a positive, and that would be the charge on a proton. So sometimes it helps to actually think of a charge on a proton or on an electron, because these are common charged particles which will move around. Sometimes it's helpful just to think of not a proton or electron, but just to think of a blob, and that could be just a little negative charge or a blob that's a positive charge, and it might not have this actual charge on it. Okay, so you're already aware of charges can affect each other. So these charged particles set up what's called an electric field around them, and it's the interaction of the two invisible fields around the particles that make them feel some sort of force. And the field has a direction. So a charged particle sets up its own electric field. So this is separate from a field that's just there in a big space. It's got its own electric field. Neutrons or charges that don't have a charge, charges that don't have a charge, I don't suppose that really makes sense, but an object that doesn't have a charge does not set up its own electric field. So a charged particle sets up its own electric field, and the field has a direction. Now the field, you can't see what the field looks like. You can't see what its own field looks like, and you can't see in which direction it goes. So we've got to imagine we're going to have this idea, and we're going to build up a picture of what the invisible field looks like, and secondly, which direction it goes in. And we're going to have a definition the direction, and this is something that physicists have agreed on, the direction of the field around a charged particle is defined as the direction of the force on an extra test So this is an extra little charged particle, and I'll draw this in a minute if this isn't making any sense, placed near to our charged particle of interest. Now that probably doesn't make any sense, but excuse me, what we're going to do is I'm going to take our charged particle of interest. Let's say I'm interested in a positive particle. Here's a positive particle, okay? And around it, it's set up its own electric field. So around it is something invisible going on that we want to determine what goes on. And whatever it is, this field, it has a direction. And we can tell what the direction is by taking an extra test charged particle. And here it is. Here's our extra test particle. And the test particle is always positive. You always work out the particle that we're interested in. We work out where its field goes by testing it with a small positive particle. So now I've got two particles. Okay, I've got the one that I'm interested in seeing what is the field around it, and I want to see in which direction it goes, and I can test that by putting in a little tiny extra positive charged particle. So our test particle is always positive. Now this particle of interest, that could become a negative particle that's got a negative charge, or it could be a neutral particle. But the test particle, for seeing where the field is and for working out the direction of the field, is always a tiny, tiny positive particle. So I'm going to now draw some diagrams. Now some of these diagrams are shown in Mr. Garrett's notes, but you have to know how to draw them. This is one of the few times where you have to actually draw a diagram in higher physics. Normally you're given diagrams, but you've got to be able to take a particle of interest, and we've got to determine what the field that is set up around it looks like, and how do we do that? Okay, so we're going to take our little test particle that I had before, and our test particle is positive. And I can stick this positive test particle anywhere I like. And if I put this particle here, because this is positive, these two positives will repel. And this little test particle, this is fixed. This is a fixed particle just at the moment. But this little tiny one is free to move. And what would happen is it would be repelled and it would shoot off in that direction. So I'd get an idea that there is something called a field line, which is drawn in by which way does this little test particle go, and it's going to go off in that direction. And then I can take another little test particle and I could stick it in just there, and it's going to get repelled because it's positive, and it's going to get repelled down here. And then I can take another one and I can stick it over here, and it's going to get repelled out there, and so on. So I will take this little test particle and I will repeatedly dot it around and see where it goes. Okay, so, and we get these in what are called field lines, imaginary field lines. So I'm going to start drawing in the field lines. Now this is what you might be given in a test or an exam, and you've got to draw the field on it, and you've got to draw the direction of the field. So we get the idea of the field by putting our test particle here, and because it's positive, it's just going to shoot straight out that way. And because it's going that way, I'm going to put an arrow on it. And if I take the one on the opposite side and I put a little test particle here, it's going to shoot off that way. And if I put another one here, it's going to shoot off that way. And same here, it's going to shoot off this way. And once you've got this idea, it's quite easy to draw this, because you're going to get these imaginary field lines. These field lines show you what the field looks like that's invisible. And it's quite simple. It just looks like spokes on a wheel. And that would be good enough, okay, to do that. So this pattern is symmetrical. In this case, this is what's called a single point charge. I'll write that down. A single point positive charge. So this is a symmetrical pattern. For a start off. And the arrows show the direction of the field. So I get the shape of the field by putting my positive test particle in. And in this case, the shape is just straight lines. This actually exists in 3 dimensions. So if you had a positive particle suspended in space, you'd see these lines coming out in all directions. So the arrows show the direction, and the field lines show you where the field is. And there are some rules for all field patterns. The rules are: field lines do not cross. And we can tell what's going on with the field, that lines that are close together, field lines that are close together, show a strong field. So here, right close up to the particle, the lines are pretty close together. You can see, you could actually measure them here on my board with a ruler, and it would be about 1 centimeter. So the lines are close together, and so the field near our charged particle the field is quite strong. Now, when you get further out to here, for instance, then the distance between the field lines is much bigger, and lines that are further apart show a weaker field. Now, I don't have space at the bottom of my board here to write that down, but what you ought to do now is write down that lines that are further apart show a weaker field. Okay, and obviously if you keep on drawing this, you don't need to necessarily draw this on your diagram, but if you keep on going right out here, then these two field lines are very far apart, and so the field gets weaker with distance. There you go. So don't forget to write in lines that are further apart show a weaker field, and get that written in as well, because I haven't got room to do that. Okay, so that's what's called the field pattern around a single point positive charge. And that's just one of the first ones that the SQA need you to know. And we're going to do a number of these. So this is the first one that we're interested in, the first field pattern. And it's around a single point positive charge. Okay, I'll rub that out, because we're now going to move on to number 2. And number 2 is a single point negative charge. And I'm going to draw my negative charge here. And I'm going to take my test charge. And my test charge, remember, for seeing what's going on to build up a pattern, is positive, remember. So if I take my test charge and put it right there, because it's positive, it's as close as it can get to the negative charge. It's actually not going to go anywhere at all, because it's already been attracted, because the positive charge is attracted to the negative charge. So I actually need to start with all my test charges. I need to start with them further away. But if I put a test charge particle here, which is positive, remember, then where's it going to go? It's just going to go straight in like that. And I can do another one over here, and it's going to go straight in like that. And I'm going to put arrows on them to show the direction. So the lines show me the pattern, and the arrows show me the direction. And my field pattern is going to evolve like this. And you'll notice a certain similarity between this one and the single point positive charge. It's exactly the same, but the arrows are reversed. So I'm just going to write same pattern as a single point positive charge, but the field direction is reversed. So these are quite easy ones to look at. We've got another 3 to go, by the way. So we've done a single point positive charge. We've got a single point negative charge. I've got another 3 field patterns that you must remember, and you must be able to draw. And you must know the principles behind how to draw them with our test particle being dropped in one by one and getting all of these lines. Okay. Right. So that's my first 2 out the way, and I'm just having a look to see where my diagrams are, because I've drawn all these out already in my lesson plan. So I've got these. I'm just finding out which piece of paper it's on. Right, okay, so that's number 2, which is a single point negative charge. Now, number 3 is where we have 2 charged particles close to each other. And I'm going to start with 2 unlike charges. And I'm going to have a negative one here. And I'm going to have a positive one here. And there's 2 of them. Now, when we had the previous 2 examples, we had that one on its own, we had that one on its own. This is when we've got 2 together. And you can probably think ahead and think, right, well, I wonder what number 4 is. It's actually 2 charges that are the same, 2 like charges. So we could have 2 negatives or 2 positives. So you can see where this is going. Okay, so we're going to take our test positive particle and think about this. We know that our test particle, which is positive, is always repelled from positive and attracted towards negative. So we might start by thinking about what happens if I just put one just there, my small positive test particle is going to get repelled from here, and at the same time it's going to get attracted towards there. So it's just going to go straight across in a straight horizontal line. Okay, what about one that I put here where it's going to get repelled, and as it goes away, now normally if it was on its own it would shoot off there, but it's going to feel the influence of this negative particle, so it's going to start to go away and then it's going to start to come back in again, and it's going to do that in a curve. And one put here is going to do the same. It's going to start there and it's going to come round to there, and these are supposed to be nice and symmetrical like that. What about one that's put here? It's going to want to go off there, but as it goes up here it will start to feel the force from this one, so it will start from here and it will go round in a bigger loop like that, and one here will go round in a bigger loop like that. And we can carry on like that. One from here will start off and it will go off like that, and it will go all the way up right off the page, and it will come all the way back down again, and it will arrive back here. So I'm going to start it off by going that way, and then it's going to disappear and you can't see where it's going, and then it's going to come back in, and it's going to come back in like that. And one going this way is going to come out like that, and I'm not going to draw it going round and round and round. I'm just going to show it coming back in there. What about one that's here? Well, one that's here is just going to get repelled, and if it gets repelled straight out, it carries on straight out like that. And if it's straight in a line here, it's not going to go into a curved path, it's just going to follow a straight path. And I want one on the other side, which is my little test particle. It gets dropped in here and it's just going to go straight in like that. And we could have some other lines as well if we wanted, as long as they don't cross over, and we put some arrows on them. So we could have them, we could have one going off like that and it's going to come back in here, and we could have one going off like that and it's going to come back in here, and we could fill in all these spaces all day long if we want. I find it easier actually to draw them coming out, but remember you need to have the arrows that show that they're going in. Okay, so there is our field line pattern with the directions of the field put on for 2 unlike charges. So that's drawing number 3. Got 2 to go. So I'm going to do number 4 now, which is what happens. There's 2 parts to number 4. There's 4A and 4B. That's when these charges are both like each other. They're what are called like charges. So number 4 coming up now is 2 like charges. Okay, and I'm going to take this out completely, and I'm going to have one charge, and I'm going to have the other one like it over here. Okay, and I'm still going to drop in my positive test particle to see what goes on. Now remember, positive test particle is always going to get attracted towards my negative charges. So let's start with one out here and one out here, a positive. My little positive test particle is just going to go straight in like that. And one out here is just going to go straight in like that. What about one that starts out here? It's going to actually follow a curved path, and it's going to go in like that. Okay, it might start off going in a straight line, but it's actually feeling a bit of force. It's feeling more from this one because it's closer, and a little bit from that one. It's going to get drawn into that one. Now, as soon as you've got one, then you can start to make the rest because it's symmetrical. And as I said, it's easier for me to draw them coming out, but in fact, the particle is going to go in. Okay, and then as I move around, just like that. Okay, so what happens right in the middle? Supposing I take my test particle, which is positive, and I put it right in the middle, in line, and at an equal distance from both of these. Well, the positive little test particle is going to feel an attracting force from that one and an equal and opposite attracting force from that one. So it's not actually going to move anywhere. So there's like a sort of dead zone in the middle here where nothing happens whatsoever between these two particles right in the middle. So there isn't a field line in the middle because there's no field line when the particle doesn't move because it doesn't follow a path. Okay, so you could put here in the middle, no field line, just to remind yourselves, as our test particle does not move. Okay, so this is our two like charges, and our two like charges are both negative. So I'm actually going to go back up here and I'm going to say both negative. And I'm going to do a sort of shortcut in a minute, and we'll have a look at two like charges that are both positive, which will be the second bit of number 4. It's pretty similar to this. In fact, it's so similar, it's exactly the same pattern, but with the arrows going in the opposite direction. And I think you ought to be able to draw this yourselves if you stopped the video and said, right, two like charges, both positive, you'd have exactly the same pattern with exactly the same little dead zone in the middle. This would change to positive, that would change to positive, and all the arrows would go back out the way. All right, so you're going to have to do that for the next one. So let's have both positive. Now I can do this pretty easily. I'm going to cheat, but you might want to draw this yourself separately, or you just might like to write the note that the two like charges that are both positive have exactly the same field pattern, but with the arrows going in the opposite direction. So I can cheat here because I've got a whiteboard, and I can add that to make a separate diagram, that to make a separate diagram. And then all I need to do is go round and take all my ingoing arrows and make them all come out. And it's quite simple with a whiteboard. So I'll just complete my field lines, go back and draw the field lines in like this. So there's all my field lines drawn again. It's exactly the same pattern, but this time when I put my positive charge, my little test charge here, it's going to get repelled and it's going to go out the way. And the same if I put it here, it's going to go out the way. And the same here. And every one of these direction arrows is opposite. So for two like positive charges, the field pattern is the same, but the direction is reversed. Now you could make this diagram 5 if you want, or you could make it 4B or something. It doesn't really matter because it's so similar. You've just got to remember just how similar it is to the two negative charges, but remember the direction arrows are reversed. Okay, that's that one done. I've got one more to do. One more diagram of field lines and their directions. Remember, stop at any time, pause, get it frozen on the screen if you're having problems. If you're able to keep up with what I'm doing whilst I'm doing it, then great. Okay. Now the last one is the field pattern. I'll call this number 6. Doesn't matter how you label them, as long as you've got all the different diagrams. Field pattern between two oppositely charged plates. So instead of having a little point charge, don't draw this, but instead of having a point charge like that, I'm going to turn this single charge into a long, thin plate. There's one, there's another, okay, and they're going to be opposite. So it's like having loads and loads and loads of positive charges. I'm going to make this have loads and loads of positive charges, and they're all joined up together. So I've only got 5, but you can imagine having loads and loads of positive charges all fixed in a long line. And over here I've got an oppositely charged plate. Now when I say a plate in 3 dimensions, it would look something like that. You'd have a plate like that, and you'd have this plate would be like that, and it's just like 2 sheets of paper, and they're called plates, 2 sheets of paper, and they're covered in, this would all be lots and lots of positives, okay, and this would be lots and lots of negatives, and these are called oppositely charged plates. I'm just drawing them side on so you can see them. Okay, so once again, how do we get the pattern? Well, you just take your positively charged test particle and you put it somewhere. Well, where are we going to put it to start with? We're going to put it, because it's positive, we're going to put it next to positive, because then you get the complete field. So if I put my little positively charged particle there, it's going to get repelled straight across there in a straight line. And let's have one we'll put there, and it's going to go straight across in a straight line. And let's have one there straight across, and we're just going to do our field pattern. Our field pattern is going to look like that. This is called a uniform field. Now, why is it uniform? Because these lines don't get any closer together. They don't get any further apart. Remember, all the other ones, the patterns look like this, where the field is quite strong here because the distance is close together. But when you get further apart, the field is weak. A uniform field is where the field has the same strength all the time. And you can tell that this field has the same strength all the time because the lines don't get any closer together. They're in fact parallel. They're parallel lines. And if they're parallel lines, then the strength of the field between there and there is the same as the strength in the field there and there, and it's the same there, and it's the same down here, and it's what's called a uniform field. Now, in the learning outcomes, it tells you about something that you don't need to know about, and it's something called the end effects. Now, it's a bit daft that they tell you you don't need to know about it, but then don't tell you what it is. So I'm going to draw in what's called the end effects and then tell you you don't need to do this. And the end effects are what happens at the ends of these plates, what happens to the field. Now, when you get right to the end, the field becomes slightly curved like that. And this is called an end effect, but it tells you what it is and then says you don't need to know about it. So I thought, right, I'll tell you what it is and then you can promptly forget it. So you don't need to know what happens at the end of these two parallel plates. Okay. Now that, I think, is the end of this first lesson. I will go straight into recording the next, and instead of getting one every lesson 3 times, you're going to get 2 of them, and we're going to go a bit faster, and you're going to get some extra stuff to do as well. So you're going to get 2 lessons, or 2 topics, if you like, in an hour lesson. And if you have to stop at the end of an hour because you need a break, and then after that half-hour break you're going on to a different subject, that's fine, but you'll need to come back to this physics later on. And as I outlined later on, you're only getting 3 one-hour lessons taught by me in effect, but you should be spending, if you were in school, 5 lessons plus 2 hours a week. 6 lessons, sorry, plus 2 hours a week, which makes 5 hours roughly, plus 2 hours, which is 7 hours. That's much, much more. It's over double what we're doing at the moment. So I will be doing another one, and you're going to have time, find time in your program to do extra stuff to jack this up from 3 hours up to 7 hours a week. All right. So I'm going to stop this right now, and when you come back to the next bit is entirely up to you. If you manage to get through this really quickly, you can start the next one. But I don't want this running over and you doing work when you should be in another class. So if you've got maths, for instance, half an hour later, you either take your half-hour break and then you definitely go to maths. You can't say I couldn't go and do the maths because I was doing physics. That's not how it works. You'll have to find some extra time in the day, and that could be in the half-hour slots, or it could be much later and you're doing stuff in an evening like you would do if you were doing homework. Okay.